this concept you saw before, let me summarize before we start with this new page. What you have to take away from that? Well, independence, I want you to be sure about it. In these 5, you'll see throughout the unit, will be assessed in any possible way in the assignment, will surely be in the exam in the form of 1 or 2 or 3 questions. So if you did not assimilate 5 or in its entirety, the whole, so, yeah?
Do we need to prove it, or do we know this
So independence is a definition. So you cannot, so it's a definition in there. What you could be asked is, suppose, it's an example, simply an example. Prove that 2 events are independent, for example. Yeah. But I will define events, and I don't know the probability there. Yes, that you can do. You might have to disprove that something is independent of the other or something else. There are many, we will see many of these examples. So I'm not, but these few pages there, extremely important. Put 5 stars there. And I'll tell you more about it through the unit. There is an example where A is independent of B, B is independent of C, and A is independent of C. Pairwise independence. If you take any pair of these events, you have independence. But if you take all of them, they are strongly dependent. Okay? This example was given here with the 2 fair coins example. So mark that one as well. The whole thing is important. Now we start a new concept. I'll start with this omega here. And how do I describe an experiment? I describe an experiment using omega and a probability. If you take more advanced units, and when things are less discrete, in the continuous case, there is something very special here that we do not. But for the moment, especially for the finite case, the discrete case, we describe an experiment with omega and p, where omega is the set of possibilities, outcomes, possible outcomes. P measures the likelihood. P is the probability. We good? Now, what is the drawback of this? Here I see a bunch of letters, or if you want, these can be strawberries, banana, apples, and so forth. It can be any object that you have in mind. Flipping of a coin, head, head. Flip twice, head, 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 tail, tail, tail. It's a bit boring, and I don't know what to do with this object. So it is good to translate into numbers. We know this is math. We know how to deal with numbers. We know how to add them, we know how to subtract, take the power, and so forth. Another reason, this object could be complex, right? Head, head, hand, tail, tail, head, tail, tail. This case is easy. These omegas are easy, but you could have something much more complicated, long. I flipped the coin many times. That case, so first, numbers are good. So what I do, I transform these into numbers. No specific thing, but I can map these into numbers. 2, these could be nice, but maybe there is too much information. I don't need all that. It's good to be economic in terms of information, efficient, if you want. So I drop what I don't care. I'm just there to count the number of tails, or the number of heads. I want to count the number of heads, so I don't need to carry these 4. 0, 1, 2, to flipping, flip twice, so these are the possibilities, right? This is an example. But then the function would be, this is mapped here. This maps to 2. I'm counting heads here, so information, okay? I deal with the information in an efficient way. So I just look at what I'm interested in. This is 0. I count the number of heads. Oh, yeah. Okay? This is an example. So what you have to bear in mind is that random variables, which is there, is simply a function. For some reason, I don't want to work with omega itself. I transfer this into something familiar or universal if you want. If I do it for any omega, I have there the real line. It's good. So I bring this in a familiar, in my comfort zone. I have numbers. In this case, it's very easy, 0, 1, 2. In other cases, it's going to be complicated. But still numbers. Are we good? Good. A function of a random variable defines another random variable. If I map again, I don't like these numbers, I like them, but if I want to work with 1, 2, 3 instead, I just add 1 to each of them, for example. I can still transform. This is not a unique way to do it. The composition of functions. But this is abstract. I want to have something concrete in mind, so I'll bring this back when I have something in mind. A discrete random variable is a real valued function. It starts being a bit, I like complex numbers as well, but in this unit, we keep it clean. Real numbers, one dimension, for the moment, one dimension. So it's just a real line. Okay? What is very, very important is the last thing. Why? Because this is the way I should consider things. If I tell you, if this is x, this function, notice that there is already something going on. In calculus, you use f for a function, g for a function. This is capital X. It's a function of omega. So, for example, capital A of ht, if this is the starting point, takes you to 1. Correct? But now, questions? It's clear? Good. So, but now, let's go backward. This is not a one-to-one function. But suppose I tell you that x is equal to 1. What are the possible omega that gives you this? So let's have an example here. Omega such that x of omega is equal to 1 in this particular example. This set here is equal to the set, to the subset of omega that is ht, th. Because these two outcomes, once you plug it in x, give you 1. Both of them. Is this clear? This is an example. What I want to, in general, is fix a set of the real line. What are the, and this is a very single outcome, but you could consider something more. What is the set of omega such that x of omega belong to this set? This is what I mean. As this was a specific example, let's continue with this example with a different choice of A. The set of omega such that x omega belongs to the interval 0.5, 3. In this example there, that one, what is this? You have to, it's going to be a subset of capital omega. Which one is it? Which one is it? Tell me. So first, this is an exaggeration. Here is a very simple model, 0, 1, 2. But I just have to count how many values fall into that interval. 1 and 2. Then for each of them, I go backwards. So this set here is going to be HT, TH, HH. That's perfect. Which is a subset of omega. Is it clear? But what is this last line saying is that, okay, nice. This is now, I explain what is this, but the information in the last line is that I cannot write this all the time. What I write instead of this is a notation, but it's very important because it's used everywhere, it's very convenient. X belongs to A. This is just, when I write this, you read this. And how you read this? In this way. Are we good? So, two things in the last sentence. I'm explaining what is this. This is a way to go back to omega. Because my goal here is to simplify a little bit, use numbers, but again, the experiment was given by omega. I need to keep an eye on what happens there. Everything was defined with omega and p. This is the experiment. I'm trying to translate it in a different language for some convenience. But when it comes to some computation, I will have to go back to what was the model to start with. And that is exactly the way I do. It's called counter image for functions. Are we good? It's clear? Now, if this is clear, I'll confuse you much less with this notation. You know what is this is already, this is difficult. And it's just a matter of notation. Okay, let's keep going. Any question? Please feel free to interrupt me at any stage. Probability mass function. I translated the omega into these numbers. I need to translate the p as well. You have two objects. You cannot just translate one of them. Otherwise, you are in trouble. So, second part of the translation. How to translate the p. But now look what happens. These are the possible values. I just need to know what is the probability of 0. So I need to tell what is. You want to have an example in mind. I did not specify p so far. Let's assume it's fair. These are fair coins. So what is the probability of 0 here? So the probability of 0 is the probability of tail, which is equal to, say, 1 over 4. That's 2 is the probability of head, because it's the only way I can get to that. It's again 1 over 4. Guess what is this? You can 1/2. So you guessed it not because you did what we did there, but because these numbers should do what? Add to 1. Okay, so we start thinking, I need to exhaust all the cases. Once you do this translation, you don't need that anymore. We use this in this translation here. Now we have a model that is with numbers. That model could be the starting point of our problems. I don't start with head, tail, tail. I can directly start with this. This is a particular example of distribution that we are going to discuss today. It's going to be the binomial distribution. with n equal to 2 and p equal to 1/2. We're going to reach that soon. So my point is, we do have to do this translation most of the time, just once. This could be the starting point of our problem. So you might have a different example. Instead of head, tail, you have a bunch of people. You assume that they are not related to each other in any sense. And you want to count how many people have some properties. For example, how many smokers do we have in this class? Now, if the probability of being a smoker is the same for each of you, of each of us, then you will have just to count instead of saying this person is a smoker, this other is a smoker, this is not. You just count. So you could have anything between 0 and all of us to be there, right? So you don't need the complete list if you're interested just to extract data from it. And you don't need the probability of each configuration, which is a lot of work. You just need the probability on the first n numbers here. So this could be the starting point of the model now. And from now on, in these pages, it is, most of the time. It's clear. No omega, or if you want, this becomes our new omega, numbers. And these are new p. Now, we do have an example here. It's Friday. I don't want to write that much. So it's the same example. Look at it. So x is the number of heads in the first tail, and it's the number of heads until the first tail. So the first one is exactly what we discussed so far. The second one, if you can read it, is something different. Here, I just flip 2 coins. Here, I flip the coins until I reach a success. And I count how many failures were there. That's a way more complicated omega. You can do the computation. If I'm waiting until the first tail, either I'm lucky and tail comes very soon. In that case, I stop there. I do not observe any head. And this happens with probability 1/2. Tail right away. Or tail in the second, as a second outcome, and head in the first one, of course, because I would have stopped otherwise. In that case, that happens with probability 1/4 because it must be HT. Or HHT, that is with probability 1/8, so forth. We will see this in detail. It's called geometric distribution. I don't care about the last one for the moment. Is this page, with the exclusion of the last one, clear? Let's talk in abstract. I just worked one example. This is not theory. This is P of 0 is equal to 1/4. P of 1 is equal to 1/2. P of 2 is equal to 1/4. I want a general setting. The name of this probability is probability mass function. Or, if you do not want to spell it, PMF. PMF. Okay? Ooh. This is a fancy Japanese, I think, chalk. Yeah, it's a good one. Okay, someone left it here. So what are the properties in general? When is P? This is an example, and you can see that I have non-negative numbers. They add up to 1, and that's more or less it. The possible value should be strictly positive. So because people do not erase. So, probability mass function P satisfies the following. P of x is larger or equal than 0. If x is a possible value, then P of x is positive, stronger. 3, if sum x, where x is possible value, of P of x, if I sum all the possibilities, this must be equal to 1. It's very simple, intuitive definition. Anything that has this can be called probability mass function, can be used to model something. Now, you know what countable means? What does it mean? Anyone?
So you can map it to the natural numbers?
Yes. So you can map it. There is a one-to-one map, or if you want, there is a bijection to be precise. Isomorphic if you want to be extreme. Bijection with a natural number. Are you familiar with this? What does it mean? So in this setting, the discrete setting is equivalent to assume that the possible values are countable. Whatever that means. But be familiar with what it means. Okay, let's start. The simple one. I just flip one coin, head or tail. Possible values are 0, 1. So Bernoulli. It's the simplest case. Bernoulli has one parameter. Can take x is Bernoulli if x can take two values, 0, 1, not 1. Probability P usually is used here, 1 minus P here. Is this of course I cannot argue anything, it's natural, 0, 1, yes or no, binary language. Is this probability mass function? Yes, as long as P belongs to the interval 0, 1. You could in principle include the boring cases, the extreme, but becomes boring. And these two things for this range of values of P are non-negative, both of them. And they add up to 1, yes, they add up to 1. Are we good? So when it's used, an experiment, single experiment, I'm just interested to see, is it a failure or success? And you can attach any value to this. I just have two possible outcomes. There is no harm to consider one outcome to be 0 and the other 1. And actually it's very convenient. Any question? Is it clear? It is convenient for me to clean the blackboards now and wait for them to dry. So I hope this was clear. I was thinking each week to give a set of very hard problems without any mark attached to it. How many of you would attempt those? Be honest. Do you have the time? Do you have the inclination to try? One person is enough. So, but you have to try. So I'll just post them on Moodle. But I want to be clear that those are just for fun. So no marks are attached, no assessment, and no use of them in the exam or any other way. And if you want to see the solution, though, I don't have time to write them down, you come to my office. We forget about this was the only one I should have erased. We forget about omega for a long time, omega and p. Now we have numbers on our side. This is good. Okay, now in the next. The binomial. I'm still thinking, why I have to choose 0, 1 here? If you like coding, you know, but there is a reason. And the reason is explained afterwards, as usually in math. You don't see it right away. It comes from a choice. Like when you play chess, you have to go a few steps farther. The reason is this one. 0 and 1, 0 as a failure, 1 as a success, is convenient. It's not just you can choose everything. Why? What are the properties of 0, 1 that are make it so convenient, so good choice? So suppose that, for a moment, for each of us, flip a coin, and if it is head is success, tail is a failure. And I'm interested just to count the number of successes. What I do, I just sum what I have. If it is 0, gives 0 contribution to the sum. If it is 1, adds 1. And when you add, the final answer is the total number of successes. Okay? What I'm going to introduce next, are you sure you can read? The light is okay? Is the sum of Bernoulli. It's also called binomial. Are we good? Now, I'm going to prove that it's the sum of Bernoulli. And it's the sum of independent Bernoulli that have the same parameter. So, binomial. X is binomial. Wait. So this is the model. It has 2 parameters, n and p. N is the number of people in this room, or if you want, is the number of trials, the number of experiments that I attempt. P is the probability of success in each of them. Possible values. Zero, very unlucky. 1, still, or n if I'm really lucky. These are possible values. The probabilities, I cannot simply write it here, there is no space. What I can tell you, if you choose k that ranges here, if k belongs to this set, then the probability mass function is equal to, I use this notation, is equal to n choose k, p to the power k, 1 minus p to the power n minus k. This is the probability mass function. Now, of course, you can use x instead of k, but I don't really care or like x actually in this, because I use x in the continuous time. Is this clear? I should be even a bit more precise, and this is equal to this, or p of x, k is equal to 0 if k does not belong to the set. But in this case, you don't need to. Just bear it in mind that if you plug in that function something else, then you get 0 as a probability mass function. This is enough. This is okay. Later in the continuous case, I will insist on the point that I just erased. Now, when this starts looking a bit complicated, so I need some tools from math. In order to analyze this, the tool is the binomial. I need to understand this binomial coefficient a bit more. And there is the so-called binomial theorem. This is not dry yet. And this is dry. Are we good? Is it clear? When is it used? When you have n experiments that look the same, they are independent of each other, and you just count the number of successes. It's actually very general. Even though I make it look a bit unique, it's very general. I need a tool in order to analyze this. What is the tool? Have you ever seen this result? And if yes, what it is? What is it? First, this is true for any A and B real numbers. It's very useful. What is it? Have you ever seen it? Nope. Okay. Are you familiar with this symbol? Everyone? Who has never seen it before? It's okay? Just raise your hand. Good. So I'm a bit puzzled by this. And I don't want to make a video out of it now. I promised another one. So I'll take some time to explain this. A few other things that come next. I'll promise a video for next week. So this, first of all, n choose k, the very definition of it is n factorial divided by k factorial, n minus k factorial. Where the factorial symbol for it simply means m minus 1, m minus 2, and you keep going until you reach 1. So 5 factorial is equal to 5 times 4 times 3 times 2 times 1, which is equal to 120. Okay? And you keep going. It grows very fast. It's really an outrageously large number. But if you have a large number here, a large number here, they compensate each other. So it's something doable, something that you can still compute. Now, why is used? Why is important? Suppose that you have 6 objects here. Let's make them 5. I find myself with the red color. I don't want to break that one. I use this. 5 objects. Okay? Actually, I shouldn't use it. These are the 5 objects. 1, 2, 3, 4, 5. They are numbered. There are 5 numbered balls. I choose 3 objects from here. How many sets different numbers I can get? I just pick 3 simultaneously. Not with any, just pick 3 of them. How many 3-digit number can I do where the order does not matter? So this is the same as 3 to 1. I pick these 3 numbers. I don't care about the order. 2, 4, 6 is a different, 2, 4, 5 is a different outcome, and so forth. How many different outcomes can you have? In this case, it's 2, but if you just pick 3 balls, what you have is 5 choose 3, if you count them. There are 5 choose 3 different ways to pick 3 different numbers out of the 5 that are written there. So as you can see, it's a very useful object. It allows you to count faster. If you just write down all the possibilities, look that this is already a bit too much, because this is 5 factorial divided by 3 factorial, 2 factorial, which is equal to 10. It's not a big number. You could have done it, but it's already a little bit of work to enumerate each of them. And if instead of 5 I use 500, it's a waste of 1 week of counting with the possibility of doing some error. So it's very useful. It's good. It's not bad. It's clear? We good? Good. Now, this definition here and the way it's used, I didn't prove it, so I'm cheating. Definitely I'm cheating. Did I prove this, that this counts the number of ways that you can choose? No. It was a kind of the prerequisite of this unit, though. So for this, I will definitely have to have a chat with you if it looks unfamiliar. And there is no problem. You can catch up very easily. Okay? So for the moment, what I'm saying is that take it for granted and let's fill the gap if it doesn't look unfamiliar for 2 reasons. It's important for this unit and it's very useful in general. Okay? It's not just for this unit. How do we use it? Let's prove this. Usually, how do you prove this? For those of you who saw it. Which I assume is the empty set here. Which is a good set. Let's start with what we have and let's do it. Usually it's by induction. Have you ever heard this expression, by induction? You use induction. We don't now because we don't have time. Induction is a lot of work. We are lazy. We use something else. Keep in mind that, okay? So we start from the other part. A plus b to the power n. How can I write it less elegantly? This is equal to a plus b, a plus b, a plus b, written n times. It's very inefficient. Are we good? Now, when I multiply out these, what can I get? I can get a to the power n in a single way. I need to multiply all of them a. When I multiply these a's, or a to the power n minus 1 times b if there is one b involved in the product. In how many ways can I choose a b? I just have to choose one of these brackets to sacrifice, like choose a b, all the rest is a. In how many ways can I do that? N ways. Look that by coincidence is n choose 1 is equal to 1. This is equal to 1. Or if you want, you have n objects, you have to choose one object, or you have n to the power n minus 2 times b. Now you have to choose 2 brackets, 2 objects among these n brackets. It's actually, to be precise, it's 2n brackets, but this is object 1, this is object 2, this is object n. Or I shouldn't use the Roman numbers here. I have to choose 2 among them to give contribution B. The rest will be A. So I choose 2. And guess what? You keep going in the same fashion. You get the sum that is on the left. This is better than induction because it tells you where it's from. But is it clear? Are we good? So I want to apply one. What is this? The sum must start from 0. If you have different things, if you start from 0, you don't end up to what is written here. This is not part. What is this? I write 1 to the power k, 1 to the power n minus k. It's the same. There is no problem. So this is equal to? Exactly. This is equal to 1 plus 1 to the power n, 2 to the power n. Are we good? This is complicated. This is simple. This you don't need, because 1 to the power k is 1. Another example. Sum. So example 2. Sum k going from 0 to n. Minus 1 to the power k, and choose k. This is equal to it's Friday, just hold 10 minutes, less than 10 minutes. Earn your freedom. So what is this? That's 0. So because here you just bring this to this side to read it in that way, you multiply n minus k, doesn't change anything. This is 1 minus 1, because it's minus 1 plus 1, if you will, to the power n, and this is 0 to the power n, which is 0, as long as n is larger or equal to 1, of course. Are we good? It's clear? Now, the third example. Now, please, these I really care.
I think that's just 1.
That's 1, you think right? This is p plus 1 minus p to the power n. Because I call this A, I call this B. A plus B is this. Sum 1 to the power n, 1. We good? And why this is, among the 3 examples, this is the only one we really care. Why? What has to do with us? What did I sum there? P, I took it from here. P is a value between 0 and 1 now. It tells us that these, if P is between 0 and 1, these are non-negative, positive. If P is strictly between 0 and 1, and they add up to 1. So that is a legitimate probability mass function. This guy here, nobody told us that they add up to 1. It's quite difficult, actually. I've been talking for 15 minutes to convince you, if I did convince you. But the thing is that these add up to 1. We spent a few minutes with other cases where you have to prove that things add up to 1. Are we good? Now, binomial, you can definitely put it on, is in the exam. is in the exam. One exercise on the binomial I always put, and this is more than a tradition, would be there. Now, at the final part of this slide, you see what I've been saying, that if you have k objects, you want to choose k objects among n ones, and choose k is what does the job. So this part, you read it. If you have never seen it, you have to fill a gap there. And it is important. Goes beyond this unit. I'm not asking you to prove this, but I need you to know also for the next units. So most probably, even if you are not required explicitly to know this, you will make some mistake if you don't know it. Or you will be at least confused by what we see. The binomial formula is what I proved for you. Now, is it okay if I jump to the discrete random variable? Do you have any question about the binomial? Question at all? Okay. Now, for the uniform, I have nothing to say other than initially, instead of analyzing what is written there, where you have m and n, I simply like the very simple. X is uniform. I just need two parameters. In this case, I put n, 0 and n. Discrete, I should add discrete uniform, because we are going to see a continuous one, which is, I think, more interesting. Possible values are these. What are the probabilities? I need to give the same probability to each of them. Yep.
Whatever plus one.
Exactly. So I need to count 0, 1, 2, 3, 4, n plus 1 object, 1 over n plus 1. Now, even though we do not need the special formula for this initial review of this random variable, which, as you can imagine, is important. If I have no information about an experiment that involves n objects, I have the tendency of initially assuming that equidistribution is the model itself. And then I refine this model later. Bayesian analysis, sometimes it's tempting to start with, I have no information, I treat all the possible outcomes in the same way. Later on in this unit, in order to analyze what happens here, we will need the following formula. And I'll prove it for you when it's needed, or you just keep an eye on it. Okay, geometric distribution. We have 1 minute. I just write to you. I just write here what I need you to know from your mathematical background. I mean, you have to fish it somewhere. So I think you saw it definitely in calculus unit. It's the geometric formula. Let's use this minute just to state it. I'm not sure if this will work here. It's wet, but let's try. Sum up to n of a to the power k, k going from 0 to n, is equal to what? 1 if a is different from 1 is 1 minus a, and then 1 minus a to the power n plus 1. Have you seen this? Never? Do you have a minute? Can I go 30 seconds? Okay. This sum here is 1 plus a squared plus a cubed plus an. If a is different from 1, do the following. Multiply and divide by 1 minus a. You didn't do anything fancy. This is 1, so it's like, I just have to be sure I don't multiply and divide by 0, but if a is different from 1, I'm on the safe side. Multiply out the numerator. 1 times 1 is 1. Minus a times 1 is minus a. 1 times a is a. Minus a times a is minus a squared. Plus a cubed minus a cubed. And you keep going. The last term is minus a to the power n plus 1. That comes from minus a multiplying a to the power n. I divide by 1 minus a, because is what I did. I kill all of this, because they kill each other. That's what they do. And what is left is 1 minus a to the power n plus 1. Later we take a limit for a. It's very nice, right? It's because this is ugly and this is less ugly. But it's very useful as well for those of you who study actuarial science. You are going to see this a lot. Okay, have a nice weekend.